Okay, hi everyone. My name is Joe Stubbs, and I am going to be talking with my colleague Smruti Padhy about how we have started using Tla Plus to explore the design of one of our software systems, Abaco. So I just want to start off with a little outline, a little overview of the talk. We'll begin with some brief introductions of ourselves, and then as part of background and framing the conversation, I thought we'd give a little introduction to the work that we do, the environment we work in, and how we kind of envision using Tla Plus for that work. And then we're going to go into some details of the effort we've done so far. So we're going to be talking about the specific software platform with Abaco that we've started using Tla Plus with, and our effort to use Tla Plus as a part of verifying Abaco certain aspects, certain properties of the Abaco system. We'll talk about the overview of our spec. We do have a Tla Plus spec for Abaco now, the invariants and the temporal properties that we've used there. And then we'll conclude with some next steps and kind of future directions for how we're going to be using Tla Plus. Okay, so just some brief introductions. So my name is Joe Stubbs. I'm a research associate at the Texas Advanced Computing Center at the University of Texas at Austin. I lead the Cloud and Interactive Computing Group. And so our group does everything from system administration to software design and deployment. And Smruti, my colleague here who has, this is a joint work, is in my group. Smruti, do you want to introduce yourself?
Hi, I am an engineering scientist in the Cloud and Interactive Computing Group at the Texas Advanced Computing Center.
Cool, thanks Smruti. So yeah, so I thought I would just begin by talking a little bit about the Texas Advanced Computing Center, TAC, where we work. For those of you who may not be familiar, TAC is really a nationally recognized academic computing center. It's technically a research unit of the University of Texas at Austin. It's not actually affiliated with the computer science department or really any other department on campus. And so while we do teach a few courses and we take some students, the primary mission of TAC is to deploy and operate advanced computing systems for the academic research community. Our flagship system is a system known as Frontera. This is a top 10 system in the world, I think top 6 at this moment, based on LINPACK style benchmarks. And it's certainly the highest ranked system at any academic institution in the United States. But we're a lot more than just Frontera. If you have used TAC systems at all, you're probably familiar with Stampede, which was our previous flagship system. Also debuted in the top 10, and it's been in production for about 5 years. But we have about 12 production class systems at this time, together with a small number, 2 or 3, 4 different kind of researchy systems, each with their own properties and optimized for different types of problems. It's also kind of interesting that we do just about everything that's involved in running a center like this, with the exception of fabricating hardware. So we manage our own cooling system, which happens to be a 50 million gallon chilled water station. We deploy and monitor the hardware. We build and optimize research codes, the actual analyses codes that are going to run on the systems. And then, and this is a large part of where my group comes in, we develop a lot of software, including web services and web applications that facilitate access to the research systems. So yeah, as I say, that's where our cloud software comes in. That's where my group comes in. So I thought we'd say a little bit about that and how we're imagining using Tla Plus, or how we've started using Tla Plus. So firstly, the users of our work are typically domain researchers. They have expertise in some specific domain of research. It could be science or domain of engineering. And they have maybe some proficiency in software, usually not a lot of expertise. Some of them have never written any code at all. And so our software tries to lower the barrier for these kinds of folks to use the advanced storage and computing resources that we deploy at TAC. On the other end of the spectrum, we do have a handful of users who are experts in programming. And so the other kind of usage modality is that folks leverage our systems for programmable interfaces to the resources to enable sort of complicated workflows, dynamic workflows, workflows that span multiple systems potentially, et cetera. So in either case, however, the key point is that the research experiments, the analyses that are done on these systems through our software really depend on the software itself. And defects in the software, in our software, can lead to errors in the scientific results. So in a way, we are a part of this problem that you've probably heard about, this reproducibility crisis that we have in not just in computational science, but really in all of science. But so our defects in our software contribute to that reproducibility crisis. And we see Tla Plus as providing really one of the first sort of truly accessible techniques for applying formal methods to our software and our designs to help reduce defects. So I'm going to start talking a little bit about a specific platform that we have begun using Abaco in. So this is our functions as a service platform, or excuse me, that we've begun using Tla Plus in. This is our Abaco functions as a service platform. And Abaco stands for actor-based containers. It is a Linux container technology based platform. So Abaco basically combines Linux container technology with the actor model of concurrent computation to provide functions as a service. If you're not familiar with functions as a service, these are becoming more popular in a lot of the commercial cloud offerings. So AWS Lambda is an example, Google Cloud Functions, all the major cloud providers have them. The basic idea with any kind of functions as a service platform is that users provide atomic units of computation, functions, to a service, and then the service runs them on its platform in response to some kind of commands issued by the user. So Abaco is a specific one that is kind of geared to the research computing community. The prototype showed up in late 2015, early 2016, and then NSF funded it officially in 2017. So at this point, we've been in production for over 2 years. We have nearly 50,000 actors that have been registered, and a number of different research projects using it. And so I think Smruti at this point I'm going to hand it over to her to talk about a little bit more about Abaco and its basic usage.
Yeah. Now to use Abaco platform, a user defines an actor by sending an API request to the Abaco system with an URL to a publicly available Docker image. Now the user then can send messages to an actor by making an API request to the URL assigned to the actor. The messages get queued in a message queue assigned to each actor. Now for each message, a Docker container is launched using the Docker image, the actor's Docker image obtained from the public registry. Now the system injects this original message into the container. Abaco collects any of these results registered by the actor. It collects all the container logs, any extra information, the resource utilization, and exposes this information to the end user through different endpoints. Now, users can also do actors update, can also delete actors, share actors with other users at a specified level, like read, execute, and update. And next slide. Yeah, so let's dive into some of the architectural details of Abaco. So Abaco consists of a distributed system of agents. So the first one is the API front ends. So it receives HTTP request from end users, processes this request, and make HTTP response back. The general runtime states of the system is stored in MongoDB, and the RabbitMQ is used as a messaging queue for communication between the agents. Spawners start and stop the workers, and the workers actually facilitate the execution of actor containers. Now each worker is assigned to exactly one actor. Then the next agent is the autoscaler. So autoscaler agent monitors the size of the individual actor message queue, and it also keeps track of number of workers assigned to each actor. The autoscaler sends message to spawners to start or stop the workers, and these messages are again brokered by RabbitMQ. So when a user actually issues an update request, the API sends a message to all the current workers or the existing workers of the actor to shut down after finishing their executions. So, so as Abaco is being used by several research projects and has been integrated into their complex scientific workflow, we have observed some issues at scale, particularly with the actor update. Next slide. Yeah. So a user to update an actor definition, the user makes an actor update API request with the updated Docker image reference URL. So all the existing workers must complete their execution with the current image. And for subsequent executions, including the messages in the queue, new worker must be started with the new image. So internally, the Abaco sends a shutdown after completion message to each existing worker via RabbitMQ, and the messages get received by workers command thread, and then the workers command thread communicates with the main thread via the shared memory. So we have observed issues when the system is under the load, that new execution were being started with a stale version of the image. Now upon inspection, we found that there is a race condition. So when the autoscaler could be actually queuing up new workers to be started at the same time, the user sends a request to update the actor. So there is a race between the new workers getting created by the autoscaler and the shutdown messages getting sent to the existing worker sent by the API. So note that here, even though it seems that the race condition is obvious, it was not, it became clearer only after we evaluated the design using Tla Plus. So next, Joe will talk about verification of Abaco with Tla Plus.
Thanks, Smruti. Yeah. So I thought we would just kind of start with a spec overview. So we did create a spec, an Abaco spec, and there are obviously different components to that spec. So firstly, we have a set of constants in the spec, and what we've observed is that those constants really serve two purposes. One is to represent configurable aspects of Abaco itself. So the Abaco runtime takes a configuration file, and that file controls different aspects of the behavior of Abaco. So you can control things like the maximum number of workers that any actor can ever have, aspects of how the scaling up and down works, etc. So that's one way in which we leverage constants. The other is to allow us to control the state space that is explored by TLC, right? And so this is things like the maximum number of messages that the system will send, the maximum number of workers, and so forth. So we observed that it was pretty easy to get a very large state space, and we needed these fine controls to make sure TLC could complete in a reasonable amount of time. Of course, we also have variables in our in our spec. These, for the most part, these represent the runtime state stored in our persistence layers, right? So the MongoDB for the actual runtime state, the status of actors, the status of workers, etc. And then the RabbitMQ to include the messages that have been queued. So the actor message queues, the command queues, etc. Then, of course, we have actions in our spec, and we've kind of classified these into two groups. Sort of one group that we're calling top-level actions. These essentially are the actions that represent the initial agents of change in the system. So this is, for example, receiving an HTTP request from a user. We have a set of actions that represent those, receiving each of those types of HTTP endpoint requests. And then we have a set of actions that correspond to the autoscaler initiating some kind of change. For example, creating workers or starting to delete workers. And then we have another group of actions which essentially represent the asynchronous activities triggered by that first group. And there are different types of these actions, including actions generated by actor executions, so workers receiving messages, becoming busy, then freeing up later. Actions generated by API requests or in response to API requests, so updating the actor, deleting the actor, and then of course actions triggered by autoscaler commands. So we were in a way sort of doing the reverse of, I guess, what would be considered best practice, right, with Tla Plus, which would be to write a Tla Plus spec and then write software. We did it the opposite way. We had a software system, and we didn't know about Tla Plus when we wrote it, but we were kind of building a spec after the fact. But our main goal was, of course, twofold: to learn Tla Plus, but primarily to kind of find and understand problems in the design. And so we used a few additional tools in Tla Plus to accomplish that. We have a couple of invariants. So the first, the type invariant, is just to ensure that all the variables maintain the correct type throughout a behavior. And then, of course, critically, this invariant that needs to say something to the effect that all workers use the image they're supposed to use when starting an execution. And this was, at the heart of the problem that we were observing in production, and it was a challenge to get this definition right. Different definitions that we tried failed, and that was understandable because it was failing in production. But ultimately, it was kind of through defining this that we were led to a good design, and I'll say more about that in just a minute. But we also have temporal properties that we heavily depended on. So primarily that all the actor messages are eventually processed. This is a key feature of the system, and that all command messages are processed. So we wanted to make sure, as we were exploring the designs, that we maintained these temporal properties. I'll also mention that we depend on weak fairness for most of our actions. We need to ensure that they eventually take place. So in finding the problem with the design, of course, we leverage the TLC model checker heavily. And as I mentioned, we realized that with our current implementation, with the current implementation of Abaco, we couldn't find a reasonable definition for this all workers use the correct image version property that would hold, right? And so we tried different ones, right? We tried different examples, such as, all workers use the same image as the actor is defined with. All workers use the same image as each other. It was kind of obvious that these wouldn't work. It's probably obvious to some of you now, but we were exploring, and so we weren't quite sure at first. But what did become clear to us was that we were going to need to modify the design of Abaco, and through that process, a reasonable working definition of the property would become clear, and that's kind of what happened. Okay, so I think Smruti, you're going to talk about this.
Yes. So So here are some of our initial outcomes. So as Joe already mentioned that we were looking into the definition of correct workers image. Like all the workers should use the correct image version. So we made several changes to the current design, and which actually leads to our new design, and in which that invariant actually gets satisfied. So one of the first changes was that the actor image revision number. So we introduced a monotonically increasing revision to an image with every update. So in the current design, the autoscaler uses the image and a flag that indicates when the existing worker should be shut down. While in the new design, the actor object saves the image revision on every update, which is in our actor update receive action. And also, workers are started with the image revision, which is in our create worker action. So the second change is the actor status changing from updating image to ready. So we observe that this is an important step, like when the actor status we are changing from updating image to ready. So in the current implementation, the first worker that is started with the new image will update the actor status to ready. While in the new design, the autoscaler moves the actor status to ready only when all of its workers have the same and the latest image. And the third change was we have added some new checks in the autoscaler for creating a new worker. So in the current design, we have workers can be created regardless of the status of other workers. While in the new design, a new worker can only be created if there is no idle workers. Next slide. And we have some more changes as well. So the next one is that we also have some new checks when deleting a worker by the autoscaler. So in the current one, the autoscaler does not delete stale workers, and the revision is not considered because the revision of an actor image concept was not there in the current design. So at the time the user issues an update, a shutdown message is sent to the current set of workers, and that is where we see the race condition. And the new design, a worker will be deleted anytime it is idle and does not have the current image revision. And finally, we modify when a worker can receive a message. So in the current one, worker's main thread receives a new message unless it is interrupted by the worker thread. While in the new design, a worker's main thread checks its revision number against the actor's revision number before retrieving the new image. So with all these changes with the we made, and in our new design, we saw that the invariant actually holds for the new design. Now, Joe will talk about the next steps.
Thanks, Smruti. So yeah, so just some first set of next steps. So we're planning to implement these design changes, code them in Abaco based on this new TLA spec. We really have a great deal of confidence it's going to just generally improve the overall system. We are also in the process of looking at the proof system for writing proof of correctness. So yeah, I will point out that earlier versions of the spec had subtle dependencies on constants. These sort of combinatorial values of different constants could make the checks pass or fail, and that was probably mostly due to just kind of bad spec code on our part. But it was it was kind of some surprise at some points to try with values 2, 3, and 4 and see passes, and then try with values 4, 5, and 6 and see failures. And so we really like the idea of having proofs that give us absolute guarantees on the properties. But of course, we will need to kind of weigh the value of those absolute guarantees with the time it takes to write the proof. So we're still in the process of writing proofs now. But in general, we're very encouraged by the results and the value that TLA Plus has provided for us, and we're planning to use it on other projects. We have other similar services, services very similar in their architecture to Abaco, such as our data transfer service, which brokers large data movement between systems, and it has a task queue and workers and a scale auto scaler, etc. So there are services that are very similar that we're planning to use it with. We're also planning to use it with our associate sites feature, which is where institutions can deploy components of our software to run in their own data centers, subsets of the components, and then in general, those components end up communicating with each other and back at the services running at TAC, via messages sent over a wide area network. So of course there are some security concerns associated with our associate sites feature, and so we're interested in using Tla Plus to verify some of the security properties. And then thinking more forward, we are interested in including Tla Plus in some of the courses we teach at UT Austin. In particular, our COE 332 Systems Design course, which is part of the Computational Engineering program, and we look at designing systems, so we think it's just a perfect fit for that, and or a potential sequel course, which we haven't written yet, but is a the design course is very popular, and I think there's a lot of demand for even a sequel. And then we, in general, are looking for ways that we can provide mechanisms and aid and encourage researchers to use formal methods in their own software. And so whether that's training or tooling or additional efforts, we look forward to finding new ways to kind of advocate and evangelize the use of Tla Plus in the broader community. Okay, so thank you very much. I think that's all we have. If you're interested in looking at the spec, there's a link to the GitHub project there, and of course a link to our own Abaco code. If you have any thoughts or questions, please get in touch. Our email addresses are there, and thank you very much.